Welcome everyone to the 2022 Photonics Spectra Conference. You're joining us now with Dr. Gerhard Holst, who is head of the Research and Science Department at Excelitas PCO GmbH in Germany. He has a background in electrical engineering and IT studies. He holds a doctorate from the University of Dortmund, working with the Max Planck Institute for System Physiology. He then joined the Microsensor Research Group at the Max Planck Institute for Marine Biology after receiving his doctorate. He joined PCO in 2001, and as head of the Research and Science Department, he is responsible for new technologies and all research. He also oversees sensor projects like the development of scientific CMOS or SCMOS image sensors. This talk is presented by Excelitas PCO GmbH, and in it you're going to hear about advancements in microscope designs that are affecting scientific camera design, as well as elaborations on some of those changes in microscopy design and future imaging advancements to see deeper into thick samples. If you have any questions or comments, please go ahead and type those into the conference chat box at any time. And if you missed part of this session, you can come back later and watch it on demand. So that's all from me for now. I would like to introduce Dr. Gerhard Holst. Welcome.
Welcome, ladies and gentlemen, to my presentation about going bigger and invisible for microscopes. Today I would like to explain a little bit how pixel size and MTF, the modulation transfer function, affect modern microscopy and give you some insight about how to look at the invisible with microscopes. But let's start. This is the overview of my presentation. First of all, I would like to define the terms I'm talking about. Then I would like to show you some examples and discuss a little bit how resolution and modulation transfer function are determined, show an example of a new camera that we were able to develop, and then show some first results of some experiments and projects we've started together with the University of Bielefeld in measuring and determining the modulation transfer functions of image sensors with the same pixel size. I would like to end then to extend our experiences to the spectral range of shortwave infrared, because that's a new range for us, and discuss and show some applications in life science in association with microscopy, how it can be applied. But let's start. The optical system I'm talking about usually is made of a sample. Some imaging optics could be objectives in a microscope or normal objectives of a camera, and finally a digital camera with an image sensor. And at the end of the camera is the typical image that we are processing, looking at, evaluating, and whatsoever. So this is the optical system I'm talking about. And it can be described by something called the modulation. And the next slide gives you some impression what this means. So assuming that we have a pattern or test target that we're looking at, some specific type of patterns are these black and white line patterns that are imaged by the objective. And at the end, in the image, you don't get the similar black and white distribution, but a more smoothed out way due to the optical system. And the finer you are making this grating or the pattern, the less contrast is in the result image. This system is described by the modulation or contrast, which is the maximum minus the minimum intensity divided by the sum of both. If you compare the image modulation with the object modulation, we achieve the real part of the modulation transfer function, or the real part of the optical transfer function, which is the modulation transfer function. So this MTF is used to describe the capabilities of an optical system to deliver sharp and high contrast images. In microscopy, usually the field of view defines the area that you can look at and that you can use for optical information. In microscopy, a larger field of view usually attempts to detect more information in a single image. And this is a benefit because you only need to record and detect less images. Therefore, in the past, usually most of the microscopes that are available on the market and used in the scientific labs had an image circle or field of view of 18 millimeters. this was perfectly combinable with the existing CMOS image sensors and cameras that usually had a resolution of 2000 by 2000 pixels with a 6.5 micron pitch, resulting in an 18.8 millimeter image circle. Just a few years ago, one company, namely Nikon, has started to redesign their optics and to allow an image circle with a diameter of 25 millimeters. This requires, instead of the former C mount, now again an F mount. And rumors say that other manufacturers as well working on these larger image circles. Now, the existing cameras do not fully use this image circle. Therefore, some manufacturers decided to develop cameras with larger sensors to more efficiently use the image circle. Some of them used image sensors with a resolution of 2000 by 2000 pixel at 11 micron pitch. This results in approximately 32 millimeter diagonal, and this fills out the image circle. But does that really achieve the benefit of the larger image circle? Let's have a look. First of all, before I come to the detailed look to that image circle, I would like to talk a little bit about the condition of reaching the Rayleigh or Nyquist criterion for resolution. Assuming a line pair of black and white lines that have a certain size or grid size, I would like to show what happens with the different sizes of the pixels. So here we assume a pixel size of one line pair. You see the drawn pixels, these are the light blue squares, and we have two use cases. One is properly aligned and one is not aligned. Now, if I have a look to the result images that are drawn below, then in both images it's clear you cannot see the structure. So we get a medium average gray value, and it's clear that this situation is undersampled. If I now go to the Nyquist condition, then I would have to assume that the pixel size is half a line pair. In the left case, where it's properly aligned, this gives a proper image. But since in a natural application where the sample is like it is, and you cannot align something in a proper way, then you would lose structures or information where the information is not properly aligned to the pixel size. Therefore, you achieve Nyquist, or you result in obeying to the Rayleigh criterion, but you cannot be sure that you catch all of the details in your image. Therefore, a more practical suggestion is to use a pixel size that is a quarter of a line pair. Because in this case, it doesn't matter whether the line pair is properly aligned or not. In the images, you are always able to differentiate and to see the structure in the image. How can MTF usually be measured? Well, one possibility is to think about and use the existing calculations, take the values from your microscope objectives, the magnification, the numerical aperture, and then do your mathematics. That's possible, but could be cumbersome sometimes. Well, another possibility is to use a very nice and efficient software that is free available, designed by Dr. Andrew Barlow, and you can download it on your smartphones, doesn't matter whether it's Android or Apple. And there you put into the parameters of your system, and you get as a result whether at this or that wavelength you are correctly sampling, undersampling, or oversampling. A third possibility is a more practical approach. You can use defined samples, whether they are test slides or biological samples with a defined size that are available from different companies, and you can use them to determine the MTF of your system and to determine whether your system is able to resolve the details that you want to look at. Here I took as an example a typical inverse microscope application with an objective, a camera adapter, and a camera, and compared some results from the software from Andrew Barlow. First use case is a magnification of 20x with an air objective with a very high aperture of 0.75, and I compared the results with a camera adapter magnification of 1 or 2. And in these tables you see the different pixel sizes or pitches. Obviously, for the standard size that is often used right now, 6.5 micron, with a camera adapter magnification of 1, all wavelengths are undersampled. Only with the camera adapter magnification of 2, starting at 525 nanometers, it looks like you have a proper sampling with the 6.5 microns. All of these applications with 11 microns are heavily undersampled. If you now increase the objective magnification or even switch to an immersion oil type of objective, then the situation becomes a lot better. But let's have a look to some specific samples. Here I compare with the same resolution, always 2048 by 2048 pixel, but different cameras with different pixel sizes. So the typical 6.5 micron pitch is what we have, and the new one that fills out the larger image circle with 11 micron pixels. And if I assume a constant photon density, then the left image with the larger pixel has a better signal-to-noise ratio due to the larger pixels. But since I now detect with a larger pixel a larger area, I see less structure, so you would see less details. Therefore, just the larger sensor without more resolution, more pixel, doesn't help at all. It fills out the larger image circle, but it doesn't give you more information. Another comparison is I use now the 11 micron pitch and compare different camera adapter magnification, because at 2x it's possible to do some imaging that fulfills Nyquist, is not undersampled, but again now you are looking to a smaller part of the whole image, and therefore you are losing the benefit of the larger field of view. This, for example, is an application where we used a 2.5 micron pitch sensor with 5000 by 5000 pixel, with which we can use as well smaller magnifications. So this was a 4x objective with an NA of 0.2, and we have recorded 55 tiles that have been stitched together with the very nice stitching feature of ImageJ, designed by Stefan Preibisch and his group. And this is very nice since it's an extremely high resolution and you can extract small parts of the image and still can see a lot of details. Even here you can count single red blood cells. Well, come back to the example of the small versus the larger image circle. Another possibility to solve that issue is to use a higher res sensor. So that's what we've done at PCO. For that purpose, we've developed the new PCO Edge 10BI CLHS. It also, with its diagonal, fills out nearly the larger image circle, but it has smaller pixels and a higher resolution. That's the way like we are going bigger now. Here you see some features of this new camera system. It has a pixel size of 4.6 microns by 4.6, 4432 by 2368 pixel resolution, and it offers 120 frames per second and uses a back illuminated SCMOS sensor with an improved MTF. The quantum efficiency is around 85%, and it has a 22.8 millimeter diagonal for large image circles. Here's a comparison of 3 color-stained sample. These were kidney cells. The standard image like achieved with one of our PCO Edge 4.2 cameras, and this would be a similar image with the new Edge 10 BI. You immediately see the larger field that you are able to detect. Let's come and discuss to something that is, well, underestimated, I would say, because usually the MTF of an image sensor is calculated from the geometrical parameters like the pixel size. This is a general way how to do that, so the maximum possible MTF usually is defined by the pixel size itself. But we have had image sensors from different manufacturers, and we've seen MTF curves that are not the same, that vary. Therefore, we started a project together with the group of Professor Thomas Huse at the University of Bielefeld to figure out how high the influence of these parameters like material, pixel structure or architecture affect the MTF. Well, these are the test candidates, so to speak, 4 different CMOS sensors, all of them same resolution, same pixel size. And then in Bielefeld, they've set up a system where they can compare 2 cameras at the same time with an image splitter. And they did a lot of tests. These are some primarily or preliminary results. They imaged test beads from tetraspec. They exchanged the camera to cancel out any influence that the system could have, and it was verified that there is no influence by the system. And here in the right graph you see the averaged MTF, so there were differences between 2 of the cameras. And finally they did all these tests with all the 4 cameras, with all the 4 sensors, and here you see the collection of MTF curves. So you see MTF can be different, although the pixel size is the same. But does that mean anything? I mean, does it have an impact to your microscopy? Well, they tested it. First application was localization microscopy with a D-storm indicator. And here you see the comparison between the 2 extreme MTF curves. And you can see a better result in the line profile readout of the right image, but it's not so distinct, which might at the end not be so surprising, because in single molecule localization microscopy you usually determine the center of the light distribution in an unsharp blob. For this calculation it doesn't matter that much if the blob is more or less sharp. Therefore, the impact of the MTF on localization microscopy is not so pronounced. But the situation is different for structured illumination microscopy. Here you use the basic assumption of the MTF as well in the calculations for the image reconstruction. And here the right image with the better MTF show a distinct and significant difference compared to the line readout of the same sample of the camera with the lower MTF. Therefore, for structured illumination, it has an impact and should be recognized and noticed before. These were my presentations about the MTF and its impact in microscopy. At the end of my presentation, I would like to cover a little bit a new spectral range. I mean, basically it's not new, but it's new for us. Therefore, shortwave infrared, what does it mean? Here you see a table that shows the whole electromagnetic spectrum from very large wavelengths at the left to very short wavelengths at the right. And you also see there is the range from radio waves, microwaves, from infrared, visible, ultraviolet, X-ray and gamma ray. There you see that at one end of the visible there is the whole range of infrared, and this is finer separated into shortwave infrared, midwave infrared and longwave infrared. As you might know, silicon, which is the material of most of the image sensors that are used in modern cameras, is not sensitive in the infrared. So it can be extended to the near infrared, but usually at 1100 nanometers, the sensitivity of the silicon stops. But there are other materials that are able to generate charge carriers in this wavelength range. And one of them is indium gallium arsenide. The interesting thing about it is, as we are not able to look ourselves in this shortwave infrared region because our eyes are not sensitive, the situations are very different for some samples. Here you see some typical comparison. Above there, the corresponding images in the visible, while down there, the corresponding images in the shortwave infrared. In apples, you cannot see the bruises or the collection of water below the apple skin, which is visible in the SWIR. As well, if the gray value of, in this case, plastic and beans is more or less the same, in SWIR, the absorption and reflection is very different. Therefore, you could much easier detect it and select them out. Same situation in wafer applications or in semiconductor applications. The silicon wafer is intransparent for visible radiation, but it's quite transparent for SWIR. Since shortwave infrared is the short end of the infrared, it's also still possible to see an increase in thermal radiation, which is shown here by the example of these soldier irons. There is, since approximately 1 year, a new manufacturer for InGaAs image sensors, which is Sony, and they benefit from their experiences in manufacturing technologies. So they have a huge experience in stacking image sensors. And with that, they are able to design and make InGaAs sensors with a much smaller pitch than it was available before. So usually before, the InGaAs sensors had 15 micron, 20 micron pitch, and now Sony is offering InGaAs sensors in 5 micron pitch. How can this be used in microscopy? Well, if you see this image in the NIR from a mouse, you can see easily that even in NIR, you can look deeper into the tissue, which fits to your own experience. If you, for example, hold your thumb in front of a lamp, then nearly you can see the light shining through your finger. Well, if you properly select the window in the shortwave infrared, then you can look much deeper into the tissue and you can generate contrast that allows to see, for example, like here, the vessels, or even other things that have been marked with proper indicators. These are some results obtained by Dr. Bruns and his group. And you see a variety of different spectral windows with a bandpass filter extracted at 1000 nanometers, 1200, 1450, and 1600. And you see that at 1450, where usually the water absorption is the highest, you get the best possible contrast. Unfortunately, you also get the smallest signal, but nevertheless, you have a lot of contrast. This can be used to really look, in this case, into living mice, so to do in vivo imaging, or in case you use proper indicators that can be selected by filters or by the selection of different illumination wavelengths, in this case 784, 890 or 980 nanometer from different lasers, and record the images with the InGaAs camera, then it's possible really, like seen here, to mark, if you use proper these indicators, to mark different organs and watch and observe them for doing research, for example, in cancer. Because of that, and because of these nice sensors from Sony, we've started to develop our own shortwave infrared camera. Here you see some images from the prototype, and it reflects what you've seen before in the movie, that it's possible to separate these different organs and look into this mouse. Just a short photograph where I'm coming from and at the moment talking to you. It's Excelitas PCO in Kelheim, Bavaria in Germany. And since '87, PCO develops and manufactures high-performance CCD, CMOS and SCMOS camera system for a lot of different applications. I'm now at the end of my presentation. I thank you a lot for your attention and I'm open for questions.
Thank you so much. And thank you everyone in the audience for your attention and for your questions and comments. If you haven't already, go ahead and type those into the chat. And thanks for joining us for how pixel size and MTF affect modern microscopy and see the invisible with microscopes. This talk again is presented by Excelitas PCO and is part of the Photonic Spectra Conference, which is hosted by us at Photonics Media. And you've just heard from Dr. Gerhard Holst of PCO. Thanks so much.